Hello everyone, you are welcome once again to my channel. This is Mr. Daniel Adjirge, your anchor person, and today we are looking at light wave. Another name for light wave is optics. So light is a form of energy that stimulates our sense of vision. Sources of light include natural and artificial sources. Natural sources of light, they are those sources that produce their own light. Okay, artificial sources also produce their own light. Yes, natural sources could be luminous, self-luminous, and non-self-luminous, meaning that some of them produce their own light and some of them they do not produce their own light actually. They depend on other sources. For instance, the sun is a natural source of light. The sun generates light as a result of burning gases or nuclear reaction present or happening in the core of the sun. The moon is non-self-luminous because it depends on light that falls on it from the sun or light that is incident on it from the sun. And that light is what the moon rather reflects to all of space or down to earth. And we see the moon's light in the night. So it's as a result of reflection of light that falls on the moon that helps us to see light coming from the moon. So the moon is a typical example of a non-self-luminous source of light. Artificial sources of light are everywhere around us. We have them from candles points or candlelight, lamp lights from our local kerosene lamp, and we also have light uh, from the electric lamp and other searchlights and torchlights and lights from different sources, whatever, or even from burning uh, materials. You can have light from there. So that is all about light. Now, rectilinear propagation of light is a phenomenon that light wave travel in a straight line. So this phenomenon tells us that light wave travels in a straight line. So if light wave travel in a straight line, so how do we describe it? So representation of light is important. So light can be represented by what we call a ray. A ray of light describes the path of light wave. So a ray of light is a tiny line or a thin line that shows or indicates the direction in which light travels. This ray of light has a line and an arrow. The arrow gives the direction of light. Of course, a light source does not produce a single ray. So all of space is filled with light from a source. So therefore, there are several rays from that source, and these rays are known as what beam. So a beam of light is therefore defined as a collection of rays of light. Of course, there are different kinds of beam. Here we have parallel beams. Here we have divergent beam, and here we have convergent beam. Convergent. Here is a ray of light indicating direction of light. Here the lines are parallel. That means the rays of light are parallel, so therefore refer to them as parallel rays. So we can define parallel rays as rays of light that are parallel, or parallel beam rather, as a rays of light that are parallel. This is divergent beam. A divergent beam means a beam of light that comes from a single point and spread into space. So we can say that a beam of light comes from a single point. That single point is called a focus. So we can describe a beam of light, a divergent beam rather, as a beam of light that emanates from a focal point or a focus. The convergent beam are beams of light that goes into a single point. That means the light rays they meet at a single point. So we can describe a convergent beam as beam of light that meets at a point. So having known this, we need to now look at the properties of light. The properties of light are reflection, refraction, interference, diffraction, and polarization. Polarization is peculiar to transverse wave because light is a transverse wave. Reflection of light is what we'll start with. Reflection of light is the bouncing back of light when light falls on a barrier in its path. So the barrier could be any object. The object could be transparent, the object could be translucent, the object could be uh, opaque. But the truth is that we need to know what a transparent material is. A transparent material allows a large percentage of light that falls on it to go through. Example of such material: water, gas, this, colorless gases like air, glass. They all allow light to go through them. A huge percentage of light that falls on them. Then there are others that allow a small amount of light that falls on them or incident on them to go through. They are called translucent. Examples are bottles. Uh, bottles are typical example. We can have a white cellophane does not really polythene material does not really allow light to pass through, but it allows a small amount, a small fraction of light or percentage of light that is incident on it to go through. So that such materials are referred to as translucent. While some materials do not allow light to go through them at all, such materials are opaque materials. They forbid light from passing through them. So we cannot view objects using opaque materials. That means we cannot see through them. But we can see through transparent material. We can view partially, only partially through translucent materials. Hope that description is okay. Now we turn from there, we want to look at the properties of light properly. We want to consider the laws of reflection. Now, the laws of reflection states that the incident ray, the reflected ray, and the normal, the point of incidence, they all lie on the same plane. So an incident ray of light is a light that meets a surface at a point. That surface is a reflecting surface. So that surface is also known as a barrier we described earlier. This ray of light makes an angle of 90 degrees with the surface. This ray of light is called a normal ray. Any ray of light that is a normal to a surface, that is a ray that makes 90 degrees on the surface on which it falls, that ray of light, after reflection, the reflected ray will travel along the same path as the incident ray. So we usually use the normal to describe reflection, because the ray of light that goes through the normal is reflected back along the same path or along the normal. Now look at an incident ray that is incident at the same point as this normal. This incident ray, after reflection, will move in this direction. That means the barrier will cause this incident ray to move in this direction. And this new direction of the incident ray is called the reflected ray. Now, the second law is what we wish to describe. The angle that the incident ray I makes with the normal, the incident ray rather makes with the normal is called the angle of incidence I, while the angle the reflected ray makes with the normal is called the angle of reflection R. The angle of reflection I is equal to the angle of reflection. So we can now state the second law as this: the angle which the incident ray I makes with the incident ray I, the angle of the incident ray I, please take note of that. The angle which the incident ray I makes with the normal is equal to the angle R which the reflected ray makes with the normal at the point of incidence. That's the second law of reflection. Let us bear this in mind. So we go back to we go back to the types of reflection. There are two types of reflection. Uh, we have the diffuse reflection and the regular reflection. This is the regular reflection, and this is the diffuse reflection. In this type of reflection, incident rays on this surface are parallel rays, as you can see. After reflection by this surface, the rays travel parallel again as reflected ray. This surface is a barrier. Such reflection is referred to as regular reflection. Smooth surfaces like in mirrors and other polished smooth surfaces always produce regular reflection or regular reflected rays. That is why when a light rays or a beam of light is shone on a mirror and that ray is incident back to our eyes, we tend to react because of the sharpness of such reflected rays or reflections. Yes, scattered reflection is from rough surfaces, not smooth surfaces. And as a result, after reflection, we do not feel the sensational impact of such reflected ray. For instance, if we cause shine a touch light or touch beam of light from a source of a beam of light from touch source of light on the wall. The light rays actually are reflected, but when they reflected or travel backward, we don't feel the reflection. We don't actually have that sensation or the effect on our eyes because the rays are scattered. So in the case of scattered reflection, we have parallel incident rays. After reflection, the reflected rays become scattered in all directions. So we say that these rays are scattered reflected or rays or diffused rays. So such surfaces that produce such types of reflection are usually rough surfaces or rough barriers. The laws of reflection have been seen before now. A plane mirror, I repeat, is formed as a result of reflection of light from a surface of glass with one side which has been coated. Now, when one side is coated with zinc paint or aluminium and the other side left untouched, that side that is left untouched is the reflecting surface. The coated part, as you can see here, is represented by these lines at the back of the straight vertical line. This vertical line is the mirror. All right. In front of this mirror is an object. To locate or to determine the image formed by this mirror as a result of this object placed in front, we need two rays that will touch the object and strike the mirror at 2 points. Suppose the ray of light touches the edge of the object and meets the mirror at this point. Another ray from another point goes through this edge of this point of the object and hits the mirror at this point. The two rays will obey the second law of reflection and will be reflected backward according to the respective reflected angles equal to the angle of incidence. So this one will be for this, and this one will cause this reflection. And now the two reflected rays are this. There is an observer down here observing, which is a viewer. He sees these two reflected rays and straight into the mirror. The two reflected rays they meet at this point. Where they meet is where the image of the object is formed. And from research, we have found that it has been known that the distance between the object and the mirror is also equal to the distance between object the object's image and the mirror. That means the distance between the image formed as a result of reflection and to the mirror is equal to the distance that the object has from the mirror. The object is always erect. The object is always erect, and the object, that by erect we mean vertical or upward. We must bear this in mind. And the object has equal distance, and the image rather is always erect. The image is virtual, not a real image. Plane mirrors do not form real images. Here we have a plane mirror here. A plane mirror, when inclined, when we have two plane mirrors inclined, we mean that they are arranged side by side, such that they make an angle. The two mirrors can form several images. As you can see here, one, two, three images are formed by this object on the mirrors. So the images are formed because of the angles they respectively make with each other. The angle they make with each other is called theta. So n is equal to 360 over theta minus 1, and that gives the angle. That gives the number of images n rather that they formed. In this explanation, I used the three images. That means I've assumed here that theta is 90 degrees. Now, if we substitute 90 here, we're going to get 360 over 90 minus 1. That will give 4 minus 1. 3 images will be formed. Here's another example where we have two uh, mirrors that are inclined at 60 degrees. So if the angle is 60, we put 60 here, obtain this result. We have 6 minus 1, and 5 will be the number of images formed. 5 images will be formed. So the angle between the two mirrors decides the number of images that will be formed. Here we are looking, we are very sure we need, we actually want B, and that's curved mirrors. Yeah, in curved mirrors, a curved mirror is formed by cutting out a vertical through a vertical plane on a glass, a spherical glass or a circular glass. When that is done, we have is we have a transparent glass cut through, then one portion is coated. The, if the back portion or the protruding part, the part that bends outwardly, is coated and the inward part is left, the inward part becomes the reflecting surface. The backward part that's coated becomes the back of the mirror. So an object are usually placed in front of the reflecting surface. In this mirror, the mirror was cut from a sphere. The sphere has a center, or a circle has a center. The distance from the center of the circle to any point on the circumference of that circle is known as the radius of the circle. So therefore, this mirror has a point called the radius of curvature. The radius of curvature is a point uh, that is the radius of curvature rather is a distance rather. There is a point on this mirror called the center of curvature, not radius of curvature. Pardon me. That point is a portion of the sphere from which the mirror was cut. That means the center of curvature is the center of the sphere from which the mirror was cut. And the distance between the center of curvature and the midpoint of the mirror is called the radius of curvature. The midpoint of the mirror is the center point of the mirror or center position of the curved arc that was cut. That point is called P. So as you can see the proper description here, we have the principal axis. Now the principal axis is a line, say any line that goes through C and also goes through P, or a line that goes through C and meets P, the pole. And so we have the description here. Student, please do well to read this one out. The principal axis. This is a line that passes through the center of curvature and the pole P. Now the radius of curvature, therefore, is the distance between the center. Please, the center of curvature C is a point. P is a point on the mirror. C is a point on the circle from which the mirror was cut. So the definition of center of curvature is a point of the sphere from which the mirror was cut. Please, it's not written here, so bear the statement in mind, the definition in mind. I repeat it, is a point of the sphere which the mirror from which the mirror was cut, or in which the mirror forms a part. So now we now say that the distance between C and P is called the radius of curvature. There's a midpoint between C and P. That point is called the focal point. The focal point is a very important point in describing curved mirrors. Now we have to concentrate on this focal point. Now the principal focus, the focal point is called the principal focus here. Now the principal focus is the principal focus of a converging mirror is the point where all rays close and parallel to the principal axis converges after reflection by the mirror. So if I have a ray of light, this ray is parallel to the principal axis. So this axis, this line is seen as the principal axis. So look at the principal axis here. So any line parallel to this principal axis, it's a ray of light, for instance. And this F has been described to us that any ray parallel to the principal axis must pass through it or must converge at it after reflection. So this is the mirror, this mirror repeated here. This is the pole, this is F. C is not shown here. But the rays of light after reflection must go through what? F. That means they must come to a focus. They must converge at the focal point. This is for the converging mirror. The converging mirror is also known as a concave mirror. Pardon me. The concave mirror, I repeat, is called the converging mirror, and that is what we are describing now. What about if the outward part is the reflecting surface and the inward part is untouched? The outward part, being the reflecting surface, will produce a kind of mirror known as a convex mirror. The convex mirror is also called a diverging mirror. In that one, the focal point or the focus, principal focus, is not a real focus. All right, we'll describe that one when we are done with this one. This one is the converging mirror, I repeat. Yeah, these are the guidelines for us to actually get images of objects correctly when they are placed in front of a curved mirror. Number one, any ray parallel to the principal axis must go through the principal focus after reflection. That was what we saw on the definition of the principal focus. Then rays that passes through the center of curvature is reflected back along the same path, that is along the center of curvature. So any ray that passes through the center of curvature behaves like the normal ray that we saw under plane surface reflection. You know that any ray that passes through the normal reflects back after reflection go travel back along the normal. So the center of curvature, any ray that goes through the center of curvature to meet the mirror, that ray is behaving like a normal ray because the center of curvature, any line that goes through it to meet the mirror, the curved mirror, that ray, it's normal, it's 90 degrees at that point of incident. We must bear that in mind. So we want to draw ray diagrams at respective positions of an object placed in front of this converging mirror. Position number one, let us consider an object that is placed at a distance at a distance away from the mirror. This is the pole of the mirror, this is the focus, and this is C. Remember, F is midway between C and P, so F is half of CP. Half of CP. So we see that F is CP divided by 2. That is the principal. The focal length, therefore, F is called, the distance between F and the pole is called the focal length of the mirror. And that F is CP divided by 2. CP is the distance between the center of curvature to the pole, and that distance we have seen before as there was radius of curvature. So when we divide the radius of curvature by 2, we will get what? The focal length of the mirror. So we must bear that in mind too. So, having known that, suppose this object is placed at a distance further away from the mirror than the point called the center of curvature. A ray of light parallel to the principal axis that is traveling to the mirror passes through the head of the object, strikes the mirror at this point. That ray of light will be reflected, and from the principle or guidelines for drawing images formed, the reflected ray must pass through the principal focus, and this is the reflected ray. Now another ray of light from the head of the object goes through the center of curvature and strikes the mirror. That ray of light will be reflected along the same path, backward again. So this is the reflected ray as well for the incident ray through the center of curvature. So the two reflected ray, this is the reflected ray for the ray that goes through the center of curvature. This is the reflected ray for the ray that is parallel to the principal axis. So the two reflected rays, they meet at this point I, and that point I is called the image, where the object's image is formed. Where the point intersects, is the head of the position of the head of the object, because the two incident rays came from the head of the object. This is the object represented by a straight line with an arrow on top of it. So this the object therefore has its head facing downward this time, and its feet up. So this time we say that the image formed by this object is turned upside down, or the proper language here is what? Inverted. The image is inverted. So that means when an object is placed in front of a curved mirror, that means a converging mirror, such that the object is some distance away from the center of curvature, the object formed is inverted, and we can see that the object is smaller than the object. We can see that the object image is inverted. This is the image. This is O, or the object. The image also is smaller than the object. This is the object. This is the image. This vertical line, small line is the image. The image is smaller than the object. It therefore means that the image is diminished. That means smaller than the object, is inverted, and it's a real image. Another thing you should note is that the object and the image are on the same side of the mirror. That means on the reflecting side. This is the back of the mirror. This is the front of the mirror. So the image formed and the object are on the same side of the mirror. So image is formed between the center of curvature and the focus, and the image is a real image. It's real because this image, when we project it on a screen or on a smooth surface, the image we see the image on that screen. So that makes the image to be a real image. Rays of light actually passes through the real image. That is why it is real. And yeah, the focal length or focal point of this type of mirror is a true focal point. It's a true focal point. So we now continue with the next diagram. In this diagram, the object is moved further to the mirror, that means closer now, but this time at the center of curvature. We cannot use guideline 2 again in plotting this object image, object image position, because the object is now at the center of curvature. So take a parallel ray that cuts through the head of the object. Sorry, this ray is not actually making contact, but actually should make contact. Cuts through the head of the object, strike the mirror at this point. That ray will be reflected through the principal focus, as said before. Now take a ray that goes through the head of the object again, but this time the ray will pass through the center principal focus. After passing through this ray is not actually passing through. It's a small error here. This ray should go through exactly. So that it will meet this line at this point. Well, after reflection, this ray will appear as parallel ray. This is the parallel ray, parallel reflected ray. So this is a reflected ray. This reflected ray is as a result of this incident ray that comes down slantly like this, and this incident ray goes through F, and then it's reflected parallel. While this parallel ray goes through the head of the object, then after reflection, we go through what? F. So with this time, we are using guideline 1 and guideline 3 to plot the diagram. These two reflected rays will meet at this point, at C again, where the object is at the moment. That means the image formed is at C, just like the object is at C. But this time the image is inverted, but at the same size as the object. So when the object is placed at the center of curvature, it will form an image. That image will be equal to the size of the object and is inverted. So we say that the magnification is 1 because the ratio of this object's size to the image size is 1. That means they are equal. So if we say 2 divided 2, that's 1. 1 ratio 1 is 1, right? 10 to 10. If the object is 10 centimeters, the image is also 10 centimeters. So the ratio is 10 ratio 10, which is 1. So that means the magnification is 1. We say that the object is exactly the same size as the image. That is for that one. Now imagine this diagram 3. This time in this mirror, we have the object move further away from the center of curvature to a position between C and F, which is the focal point. This is the focal point. This is the focal point where you can see that red dot and pink dot, and this is the other points called the center of curvature, like I've been stressing. Uh, Now, a ray of light, this is the object. Now, a ray of light can now pass through the center of curvature since the object is no longer at the center of curvature. We take a ray of light, an incident ray of light travels through the center of curvature, goes through the head of the object. It will be reflected back according to that principle that any ray that goes through the center of curvature must return along the same path. So this is also the reflected ray. Here as you can see where the indicator is at the moment. Now take another ray of light parallel to the axis, goes through the head of the object again as before, as usual. After reflection, because it's parallel to the principal axis, must pass through the focal point. So it's reflected backward to the focal point. This is focal point. And after reflect, this is the reflected ray. So the two reflected rays are this one. So we have to extend them backward until they meet. Where they meet, that is where the object image is formed. So this is the object image. Alright. So we can see that we have I here, object image. Here we have O, object. The object is standing upward, but erect, that is vertical or upright. But this one is vertical, but it's inverted. The head is not down because why is the head down? I explained earlier on that the two incident rays came through to the mirror from the head. So where the two reflected rays meet will form the head of the object and the head of the image. So that is that. So if the image is formed here, an image is also inverted like in the last case or the two previous cases that we have seen so far. So therefore, we can see that the image is also inverted. Excuse me. The image is bigger than the object. Where we say that the image is not magnified. The image is bigger than the object. Wow. By far bigger than the object. So this is position 3. So we proceed from there. Now look at this one. Yeah, the object is moved yet further, but this time it's placed at the principal focus. So we cannot, we just take a ray of light parallel to the axis, goes through the head of the object. After reflection, the ray of light also passes through the principal focus. Take another ray of light from that passes through the center of curvature. That ray will go through, hit the mirror and reflected back along the same path, following the old principle. But the two reflected rays, this one is coming like this. This is the incident ray that causes this one. The two reflected rays, we can see that they will never touch. They never touch. Okay, they did not meet. They will never touch. They remain parallel forever. So the image, and the two reflected rays cannot meet, which means they cannot form an image, or the image will be formed at a distance. That distance is called what? Infinity. So the image formed cannot be seen on the screen because the image does not what? Exist. It exists at a distance. So we say the image is formed at what? Infinity. Images at infinity. That is a language here. We must bear in mind, these are exam questions. When the object is placed at the center of curvature, we saw that the object's image is the same size as the object. But this time, when the object is now at the focal point, the object does not have an image. So the last position is when the object is between the focal point and the mirror itself, or the pole of the mirror itself. That's where we are going. That's where we are heading to. Now, this is the position where the object is between the focal point and the pole. Here we can see that the image formed is this one, I. First of all, take a ray of light, strike the mirror. That ray of light will be reflected according to the same principle through F. Look at the F. That means the reflected ray is cutting even through the object. This cannot be a reflected ray. Look at another ray. Take another ray from C, goes through the head of the object, strikes the mirror, it's reflected back. And when we project these two lines backward, they will spread out, they will never meet behind. But when we project them back forward into the mirror and using broken lines forward into the mirror, they will meet at this point where the image is formed. So the observer sees the image this time behind the mirror, unlike the previous cases where the image is always on the same side of the object. But this time the image is on the opposite side. That means the image is behind the mirror, not in front of the mirror, like in the other ray cases. So this type of image form is not a ray image. We can see that the point of intersection is this, and that will be the head of the object because the two incident rays they came from the head. So the two reflected rays must also intersect at the head. So where they intersect is at the head. So that is this time the object for the first time has an image that is standing erect. That is an image that is upright rather. Upright. Erect means in all cases the image is standing erect but inverted. But this time it is standing upright. The head is upright. So that means this image is a unique one in the sense that it's not a real image, and so this image cannot be seen on the screen. So this is the only condition where a concave mirror can form an image that cannot be seen on the screen, and this image is a virtual image. A virtual image is not a real image because it cannot be seen on the screen. And we can also notice that the virtual image is magnified, it's also bigger than the object. So that concludes the concave mirror or the converging mirror. Let us look at the convex mirror briefly. The convex mirror is this one. In the convex mirror, in the previous description, this time the inward part of the sphere or glass is shaded or coated, leaving the outer part as a reflecting surface. So the outer part is where rays of light can fall on and reflection can happen. So inside the mirror, that is where we have the focal point and the center of curvature. That makes the focal point to be inside the mirror, at least at the back of the mirror, and that makes the focal point not to be a real focal point. So this mirror has a focal point that is not what real. Here is the object. So an object is placed in front of this mirror. At any position, the image formed is usually diminished, irrespective of the object's position. So we only have one ray diagram for this mirror type. And look at the object. A ray of light strikes the mirror at this point. The ray of light, after reflection, will appear to diverge from the principal focus here. So the principal focus of a convex mirror it differs from that of a diverging mirror. So we can define the principal focus of a convex mirror at that point where rays of light parallel to the principal axis, parallel and close to the principal axis, tend to diverge or spread out from after reflection. So if we do that, therefore after reflection, this ray after reflection will appear to be coming from the back of the mirror, from the focal point behind the mirror. So this is the focal point behind the mirror. The rays of light, sorry, look at it. This is the focal point, look at it. So the ray of light goes like this. This is the reflected ray, as seen by this yellow arrow. This is also the reflected ray from the center of curvature. So take a ray from the from the head of the image, goes through straight to the mirror. Its incident after reflection must also pass through the center of curvature. So the rays appear to be coming from an untrue center of curvature. That means this is the center of curvature. The ray tend to move like this through to the head of the object. So the image form is actually upright too. It's upright. So at any position, the image is upright. It's not inverted. So this image is usually upright. The image of this object is usually upright if the object is placed in front of a convex mirror. Okay, the convex mirror is also known as a diverging mirror. Please take note because here the rays of light diverge from a point, from the focal point. Unlike in the previous one that we saw, the converging mirror, the rays of light converge or passes through the principal focus. In this case, the rays of light, I repeat, diverge or spread out from the principal focus. I repeat, one of them, the rays of light, they will come to a focus at the principal focus, that's the converging one. By the other one, the rays of light will move from the principal focus that will spread out, which is this one that we are dealing with. So that is for this type of mirror. So there we are. The principal focus of a convex mirror is defined as the point where all rays close and parallel to the principal axis diverges or spread out from after reflection. So we must bear that in mind. Alright? That all rays tend to diverge from this point after reflection. So that is for the concave mirror. We are still here. We need to now look at how these mirrors, uh, their images can be formed in terms of analysis or analytical method. Now, before we do that, before we go into the calculation, we have what we call the mirror convention. In the mirror convention, there are two. We have the real is positive convention, which is on board. That's the one we are going to deal with, and the new Cartesian coordinate or the new Cartesian system. In this real is positive convention, we are going to see that all in determining the nature, position, and size of the image formed by this mirror, we are going to consider positive values for real focal points, negative values for virtual focal points, positive value that is plus for real images, and negative values for virtual or non-real image. Please take note of that. A concave mirror can produce both real and virtual image, but a convex mirror can only produce virtual image because a convex mirror has virtual focus or focus that is, or principal focus that is not real. That means its focal length will be minus or negative. While a concave mirror, I repeat, produces both real and virtual, but its focal point is real. Therefore, its focal length is always real, and its focal length will be positive. So the focal length is f. We have seen that the objects are placed at a distance away from the pole of the mirror. That distance the object is from the pole of the mirror is what we refer to as what u, object distance from the mirror, and then we are going to call v the image distance from the mirror in this study. So here we have a really positive convention, and it can be shown that the focal length of the mirror, the object distance, and the image distance are related by the formula. So u is the object distance, u is object distance from the mirror, that is the object distance from the pole. V is the image distance from the mirror, which is the image distance from the pole, and f is the focal length. Focal length is the distance between the pole and the focal point. Please take note. We have already seen before now that the focal point is midway between the center of curvature and the pole, and so the focal length is half of the distance between the radius of curvature, because radius of curvature is the distance between the center of curvature and the pole. So we take note of that. The magnification is a ratio that connects the object size, how big the object is, to the image, or how big the image is rather to the object. The ratio of the image size or image height to the object. So we can even extend this by describing magnification m of the mirror as the image height over object height equal to the image size over object size, and this is also the same as the image distance over the object distance. So that means we have a chain here of expression. So now we say that v over u is image distance over object distance, can also give us the magnification as seen in this statement here. So we have to apply this to some simple problems and analytically. Let us see how we can apply this idea. Now, here we have a problem. A concave mirror produces a magnification of 2 when an object is placed 20 centimeters from its pole. Determine the focal length of the mirror and the nature of the image formed. Now, the magnification is already given to us as 2. The object distance is 20, and that means u. So the magnification, according to the last expression, m is equal to v over u. So that means m is 2 and u is 20. If we cross multiply that, we will get v as 40. But that is not what they want us to find. V is the object image distance. Image of the object, its distance is 40. But that's not what they want us to find. They want us to find the focal length of the mirror. So the focal length, using the mirror formula that we have seen, 1 over f is equal to 1 over u plus 1 over v. And if we go straight and substitute the respective values, we will get 1 over 20 plus 1 over 40. Let us add this using fraction. 20 plus 20, the LCM of 20 and 40 is, between these two is 40. So if 20 go and divide this, we'll get 2. 2 times 1 is 2. 40 go and divide 40 is 1. 1 times 1 is 1. That means 3 over 40. Then if we follow the simple rule of inversion, let f goes up and 1 comes down. That means 3 will go up, down, and 40 will go up. That will give us f equal to 40 over 3. That's the first example. In the second example, we have this. The focal length of a convex mirror is 15 centimeters. Full stop. At what distance would an object be placed so that it produces an image 6 centimeters from the mirror? So the focal length is given as 15 centimeters. But the problem is this: we must note the type nature of the mirror. This time the mirror is a convex mirror. Take note, in the last example, it was a concave mirror, which is a converging mirror. So we took f as positive. But this time, we must take our f as negative, since we are following the real is positive convention, which states that the mirror that has a positive focal length minus plus will be attached to it. Okay, which we did the other time. We did not bother to add the plus to the concave lens because the previous example, because positive is positive, we don't need to add the plus sign. But this one is negative focal length because the mirror is a convex mirror. So this one we put minus 15. The image is formed 6 centimeters, and so therefore the image is always formed behind the mirror, at the back of the mirror. So the image distance is minus 6. Then using 1 over f is equal to 1 over u, we shall now get the value of 1 over f minus 1 over v is equal to 1 over u. Because we are looking for the object distance, which is u, we make 1 over u the subject of what formula by moving this 1 over v to the other side to go and meet f. This plus changes to minus. That is what you are seeing here. So if we find if we add this using fraction, okay, simplify this using fraction, the LCM of f and v is fv. If f goes into v, it will give us, if f rather goes into fv, f will cancel f from fv, and that will leave v alone. So v times 1 will give us v. If v goes into, go and divide fv, v will cancel v, leaving f. So f times this 1 will give us what? F. So we get v minus 1. Sorry, v minus f all over fv will be equal to this what? 1 over u. That is why but here we wrote the 1 over u first. So 1 over u is equal to v minus f, fv. Now we now need to substitute. F is minus 15. We go and put minus 15 there. But we start with v. It is v minus f. So v is minus 6, right? In place of this one, minus 6. Then this minus is this one. And then we come and write a bracket because this f is minus. Put a bracket and write the minus 15 there. And then we come under and say fv means f times v. That means minus 6 times minus 15. That will give us 90. Minus 6 plus 15. How did we get this plus here? Minus times minus we change to plus because of this bracket. So that means minus 6 plus 15 will give us what? Will give us 9. So that means we have 9 over 90. So 1 over u is 9 over 90. If we change it, let u go up and 1 comes down. Let 9 goes up and 90. 9 comes down and 90 goes up. That will be 9 over 90. And if we divide, we get 10. So u is 10. Or simply we can divide 9 here, 1. 9 into 90, 10. So we get 1 over u equal to 1 over 10. So 1 and 1 on top. U and 10 on top. So therefore the denominator will be equal. U is equal to what? 10. Because the numerator is 1 and 1. So that is that. Or we can simply say inverting. U goes up, y1 comes down. So 10 goes up and 1 comes down. So that is that. So yeah, the convex mirrors are used as driving mirrors. This is due to the fact that they have a wide range of view. So driving mirrors for cars and vehicles are convex mirrors. That's one application of mirrors. I hope you do grab a lot from this lesson. You can communicate me should there be any question in mind. Thanks for watching and listening at the same time.